Good day, everyone. We are the Group 3 and we are assigned to report Chapter 6, which is all about hydrographs. So, as we all know, in the previous chapter, long-term runoff concerned with the estimation of yield was discussed. This chapter, meanwhile, it examines in detail the short-term runoff phenomenon and it primarily focuses on the storm hydrograph. So, consider a concentrated storm producing a fairly uniform rainfall of duration d over a catchment. After the initial losses and infiltration losses are met, the rainfall excess reaches the stream through overland and channel flows. In the process of translation, a certain amount of storage is built up in the overland and channel flow phases. This storage gradually depletes after the cessation of the rainfall or after ning stop ang uwan. Thus, there is a time lag between the occurrence of rainfall in the basin and the time when that water passes the gauging station at the basin outlet. The runoff measured at the stream gauging station will give a typical hydrograph as shown in figure 6.1, which I will show in the next slide. So, the duration of the rainfall is also marked in this figure to indicate the time lag in the rainfall and runoff. The hydrograph of this kind, which results due to an isolated storm, is typically single-peaked skew distribution of discharge and is known variously as storm hydrograph, flood hydrograph, or simply just hydrograph. It has three characteristic regions. Mainly, we have first the rising limb AB joining point A, the starting point of the rising curve, and point B, the point of inflection. Then we have second the crest segment BC between the 2 points of inflection with a peak P in between. And lastly, we have the falling limb or depletion curve CD starting from the second point of inflection C. So, mao na ang atong figure of a flood hydrograph. Typical figure ni siya sa flood hydrograph or storm hydrograph of an isolated storm. So, mao na ang elements of a flood hydrograph. So, atong x-axis nagrepresent of time in hours. Meanwhile, ang atong y-axis is discharge in cubic meter per second. So, first, mao na ang atong bar graph sa atong rainfall nga giproduce sa atong storm. As we can see, concentrated storm producing a fairly uniform rainfall of duration d. Then we have MA or the base flow recession. Next is the AB. From the name itself, the rising limb mao ni. Then we have the crest segment BC or also known as inflection points nga na ay peak or P sa to nga mo ni ang kinatas-an nato na point. Then we have the CD or the falling limb, as you can see. Then we have the DN, the base flow recession, and of course ang atong direct runoff. Then sa ubos na pud tay base flow or mo ni ang point na ang atong uwan kay ning infiltrate na sa atong soil or ground. Mao na ang atong base flow is also known as groundwater flow. So mo na ang figure of a typical flood hydrograph. So, the hydrograph is the response of a given catchment to a rainfall input. So, it consists of flow in all three phases of runoff. We have surface runoff, interflow, and base flow, and embodies in itself the integrated effects of a wide variety of catchment and rainfall parameters having complex interactions. The interactions of various storms and catchments are, in general, extremely complex. If one examines the record of a large number of flood hydrographs of a stream, it will be found that many of them will have kinks, multiple peaks, resulting in shapes much different from the simple single-peaked hydrograph as shown in this figure. So, ani nga hydrograph, di ra ni siya mao atong hydrograph because magdepend man ang hydrograph sa storm characteristics nato. So, kani simple ni siya na apud tay mga complex hydrograph. So these complex hydrographs are the result of storm and catchment peculiarities and their complex interactions. Next, we have 6.2, which are the factors affecting flood hydrographs. So naa si Jai, gigroup si Jai into two. We have the physiographic factors and the climatic factors. So first, we have physiographic factors, which consist of basin characteristics na si Jai shape, size, slope, nature of the valley, elevation, and drainage density. Then number 2, we have infiltration characteristics, which consist of land use and cover. Then we have soil type and geological conditions, and lakes, swamps, and other storage. Lastly, we have channel characteristics, cross-section, roughness, and storage capacity. Then we have for the climatic factors, storm characteristics, naatay precipitation, intensity, duration, magnitude, and movement of storm. Then second, we have the initial loss, and lastly, we have the evapotranspiration. So generally, the climatic factors control the rising limb and the recession limb is independent of storm characteristics being determined by catchment characteristics only. So, most of the factors nga listed ani nga table are interdependent. Further, their effects are very varied and complicated. So, let's first discuss physiographic factor. So first, we have the shape. So, the shape of the basin influences the time taken for water from the remote parts of the catchment to arrive at the outlet. So, this is why naa ning occur ang atong peak kadto ang gipakita ganiha nga kani si Jang P mo to hinungdan nga mo-occur ni ang atong peak, and hence the shape of the hydrographs are affected by the basin shape. So, fan shape, nearly semicircular shape catchments give high peak and narrow hydrographs, while elongated catchments give broad and low peak hydrographs. So, nata dire tulo ka figures A, B, and C. Mo na yung atong hydrographs from three catchments having identical infiltration characteristics due to identical rainfall over the catchment. So, in catchment A, makita nato, the hydrograph is skewed to the left and the peak occurs relatively quickly. As you can see, dali ra atong rising limb, then occur na dito ang atong peak. So, mo to giingon na nearly semicircular shape catchments give high peak and narrow hydrographs. While in figure B, dugay pa ang atong pagsaka sa atong peak. So, the hydrograph is skewed to the right, the peak occurring with a relatively longer lag. So, dugay ang atong lag time. So, makita na to nga difference siya sa figure A. Dugay ang atong rising limb, like taas siya, usa pa ning abot sa atong peak. Then, we have lastly, for figure C, indicates the complex hydrograph produced by a composite shape. So, as I've mentioned earlier, di ra kay simple hydrograph ang atong ma-encounter because naaman tayo different characteristic of storm depende og unsa iyang pag-occur og way sa pag-occur. So, kani mahitabo ni ang kani na figure, kaning figure C, mahitabo og kuan mo-occur ang storm simultaneously. Duha ka storm mo-occur simultaneously. That's why ingani ang shape sa atong makita duha kibali ang atong peak. So that's all about shape. Then next we have the size. So small basins behave different from the large ones in terms of the relative importance of various phases of the runoff phenomenon. So in small catchments, the overland flow phase is predominant over the channel flow. So of course, kay small man atong catchment, so mas dali jud motaas ang atong tubig. Hence, the land use and intensity of rainfall have important role on the peak flood. So, on large basins, meanwhile, these effects are suppressed as the channel flow phase is more predominant. So, bali na pod og large basins or catchment. The peak discharge is found to vary as A raised to the power of n, where A is the catchment area and n is an exponent whose value is less than unity, being about 0.5. So the time base of the hydrographs from larger basins will be larger than those of corresponding hydrographs from smaller basins. So the duration of the surface runoff from the time of occurrence of the peak is proportional to A raised to the power of m, where ang atong m is an exponent less than unity and is of the order of magnitude of 0.2. Next, we have the slope. So the slope of the main stream controls the velocity of flow in the channel. And as the recession limb of the hydrograph represents the depletion of storage, mo na tong pag-ubos na sa atong discharge. So ninggamay pod ang atong water bale. So the stream channel slope will have a pronounced effect on this part of the hydrograph. Large stream slopes give rise to quicker depletion of storage and hence result in steeper recession limbs of hydrographs kibali taas ang iyang ginaugan. This would obviously result in a smaller time base. The basin slope is important in small catchments where the overland flow is relatively more important. So in such cases, the steeper slope of the catchment results in larger peak discharges or taas-taas ang atong kuan, peak or P. Then we have the drainage density. So drainage density is the ratio of the total channel length to the total drainage area. So large drainage density creates a situation conducive for quick disposal of runoff down the channels, while smaller density basins, meanwhile, the overland flow is predominant as mentioned earlier, and the resulting hydrograph is squat with a slowly rising limb. So as we can see, mao ni ang atong low density kaning broken line. So slowly rising limb ang atong makita, whereas sa kaning high density taas dritso ning saka na siya padong sa atong peak. Then we have the land use. So vegetation and forests increase the infiltration and storage capacities of the soil, as well as cause considerable retardance to the overland flow. So atong every action sa atong vegetation and forest can cause effect na sa atong soil. So the vegetal cover reduces the peak flow, small catchments of area less than 150 kilometers squared. So atong vegetal cover prominent ni siya in small storms. So two catchments of equal area. Therefore, other factors being identical, the peak discharge is higher for a catchment that has a lower density of forest cover. So ang land use mo ni siya ang atong only factor that can be manipulated and represents the only practical means of exercising long-term natural control over the flood hydrograph of a catchment. So land use man, so kita may nagdictate ug unsay mahitabo ana kay kita may nagamit sa atong land. So mo nang giingon nga it is the only factor that can be manipulated kay unsa ang atong paggamit sa land, magdepend po diha ang effect og naanay rainfall or storm. So lahi-lahi pod ang atong hydrograph. Then we have the climatic factors. So among climatic factors na ay tulo ka pinaka most important nga factors affecting the shape of a flood hydrograph. Mao ni ang intensity, duration, and direction of storm movement. So for a given duration, the peak and volume of the surface runoff are essentially proportional to the intensity of rainfall. So this aspect is made use of in the unit hydrograph theory of estimating peak flow hydrographs, which will be discussed in the next subtopics na. So in very small catchments, the shape of the hydrograph can also be affected by the intensity. So the duration of storm of a given intensity also has a direct proportional effect on the volume of runoff. So the effect of duration is reflected in the rising limb and peak flow, as you can see man sa atong figure nga gipakita. So ideally, if a rainfall of a given intensity I lasts sufficiently long enough, a state of equilibrium discharge proportional to IA is reached. So if the storm moves from upstream of the catchment to the downstream end, there will be a quicker concentration of flow at the basin outlets. So this results in a peaked hydrograph, or like kadtong taas ang atong hydrograph, pataas si og porma nga na atong peak. So conversely, if the storm movement is up the catchment, the resulting hydrograph will have a lower peak and longer time base or lag time. So this effect is further accentuated by the shape of the catchment, with long and narrow catchments having hydrographs most sensitive to the storm movement direction. So mao to si Jang atong climatic factors. The next subtopic is all about components of a hydrograph, which napakita na to sa introduction ani nga chapter 6 kadtong figure. So again, ang atong components of a hydrograph na itulo, we have the rising limb, crest segment, and recession limb. So diri na subtopic ma-discuss in detail ang kani nga mga components. So first, we have the rising limb, so also known as concentration curve. So rising limb represents the increase in discharge due to the gradual building up of storage in channels and over the catchment area. So again, from the name itself, rising limb, mauni ang atong pagtaas sa discharge. So the initial loss and high infiltration losses during the early period of a storm cause the discharge to rise rather slowly in the initial periods. So as the storm continues, more and more flow from distant parts reach the basin outlet. So simultaneously, the infiltration losses also decrease with time. So under a uniform storm over the catchment, the runoff increases rapidly with time. So thus, the basin and storm characteristics control the shape of the rising limb of a hydrograph. So that's all about the rising limb. Again, napakita na to si Jia sa atong figure. Ganiha mo to ang pagtaas sa atong discharge. Next, we have the crest segment, or also known as the points of inflection. So it contains the peak flow, which occurs when the runoff from various parts of the catchment simultaneously contribute amounts to achieve the maximum amount of flow at the basin outlet. So for large catchments, peak flow occurs after the cessation of rainfall, or after pag-stop na sa atong rain, the time interval from the center of mass of rainfall to the peak being essentially controlled by basin and storm characteristics. So multiple peak complex hydrographs in a basin can occur when two or more storms occur in succession. So as I've said earlier, atong figure C, kadtong duha kibali ang peak sa atong hydrograph, mo to mo-occur siya og two or more storms occur in succession or simultaneously. Lastly, we have the recession limb. So the recession limb, which extends from the point of inflection at the end of the crest segment C. So you can see kani dire mag-start ang atong recession limb to the commencement of the natural groundwater flow D. So recession limb represents the withdrawal of water from the storage built up in the basin during the earlier phases of the hydrograph. So while ang atong rising limb mao ni ang pagtaas sa atong discharge, ang atong recession limb or also known as falling limb mao ni ang pag-ubos or withdrawal of water from the storage. So we can see na maatong pagnaog sa atong line graph mo ni ang atong recession limb. So the starting point of the recession limb, the point of inflection, represents the condition of maximum storage. So diri ay ang atong maximum storage at point C. So since the depletion of storage takes place after the cessation of rainfall, the shape of this part of the hydrograph is independent of storm characteristics and depends entirely on basin characteristics or sa atong catchment. So the storage of water in the basin exists as, first we have the surface storage, which includes both surface detention and channel storage. We have second, interflow storage, and lastly, we have groundwater storage or base flow storage. So Barnes, 1940, showed that the recession of a storage can be expressed as Q sub T is equals Q naught times K R raised to the power of T. So, in which ang atong Q sub T is the discharge at a time T, given time ni siya, and Q naught is the discharge at time 0. So, ang atong K sub R is a recession constant of value less than unit T. So, ang atong K sub R magdepend ni siya sa kind of storage, kani surface storage ba siya, interflow storage, or groundwater storage. So equation 6.1 can also be expressed in an alternative form of the exponential decay as Q sub T is equals to Q naught times E raised to the power of negative AT, where ang atong A is negative ln K sub R. So the recession constant K sub R can be considered to be made up of three components to account for three types of storages as kadto halagang giingon ganiha kaning surface storage, interflow storage, o groundwater storage. So ang atong recession constant K sub R is equals to K sub Rs times K sub Ri times K sub Rb, where K sub Rs is recession constant for surface storage, K sub Ri is recession constant for interflow storage, and K sub Rb is recession constant for base flow. So typically, the values of these recession constants when time t is in days are, for K sub Rs, we have 0.05 to 0.20, and for K sub Ri, we have 0.50 to 0.85, and lastly, for K sub Rb, we have 0.85 to 0.99. So when the interflow is not significant, K sub Ri can be assumed to be unity or kadtong 0.05. So if suffixes 1 and 2 denote the conditions at two time instances T sub 1 and T sub 2, then we have from equation 6.1, so mahimo ni siyang Q sub 1 over Q sub 2, which mo ni atong mga discharge, so equals K sub R raised to the power of T1 minus T2, or T sub 1 minus T sub 2. So, mo ni mahimo na to nga equation 6.2. Or from equation 6.1a, we have q sub 1 over q sub 2 is equals to e raised to the power of a times the quantity of t sub 1 minus t sub 2, which makes our equation 6.2a. So, equation 6.1 as well as equation 6.1a plots as a straight line when plotted on a semi-log paper with discharge on the log scale. So, the slope of this line represents the recession constant mo to ang atong k sub r. Using this property and using equation 6.2 or 6.2a, the value of k sub r for a basin can be estimated by using observed recession data of a flood hydrograph. So, ang atong storage S sub t remaining at any time is obtained as S sub t is equals to the integral of q sub t dt from t to infinity is equals to the integral of q naught times e raised to the power of at dt again from t to infinity is equals to q sub t over a. So, mo ni ang atong equation 6.3. So, that's all about the components of hydrograph and the first two subtopics for